Section 8.4, we're going to outline the basic quantum mechanical approach to deriving molecular orbitals from atomic orbitals. We'll describe traits of bonding and anti-bonding molecular orbitals. We're going to calculate bond orders. We're going to write some molecular electron configurations for first and second row diatomic molecules. We'll relate these electron configurations to the molecule stabilities and magnetic properties. So first, the magnetic properties. Molecules that have unpaired electrons are attracted to strong magnetic fields. This is known as paramagnetism. Molecules that have all paired electrons weakly repel magnetic fields. This is known as diamagnetism. This phenomenon can be measured by a magnetic susceptibility balance. This technique measures the precise mass of a sample in the presence of magnetic fields of varying strengths. So if we picture that I put a sample inside of a container and I can accurately weigh its mass, obviously we wouldn't use one of these, we'd have like a electronic balance, and I put it in between two magnets, electromagnets, where I can control this magnetic field and vary it. I can measure the magnetic susceptibility of that compound by seeing how the mass changes as I vary the magnetic field. Molecular orbital theory. So far we have been talking about overlapping atomic orbitals forming bonds. In molecular orbital theory, those atomic orbitals actually combine together to form a new orbital that encompasses a larger part of the molecule. Molecular orbital theory describes bonding and electron density as molecular orbitals. The molecular orbitals are similar to atomic orbitals, except they span an entire molecule. The behavior of the electrons is described by the wave function that we talked about before, and it's limited to discrete quantized energy levels. The probability of an electron being found in a region around a molecule is described by the product of the complex conjugates of the wave function, which we're going to write as psi squared. Psi squared determines the shape of the molecular orbitals. You always wind up with the same number of molecular orbitals as you had atomic orbitals to begin with. So atomic orbitals are combined to form an equal number of molecular orbitals. The mathematical process of combining the atomic orbitals is called linear combination of atomic orbitals, LCAO. And LCAO is a special case of the law of superposition, which you may learn about in differential equations. Combining these wave functions can lead to constructive interference, resulting in regions of higher electron density, and it can also lead to destructive interference, resulting in regions of lower electron density, exactly as we saw for electromagnetic waves. In phase and out of phase combinations. So our in phase combinations produce lower energy sigma s molecular orbitals. The out of phase additions produce a higher energy sigma star s molecular orbital. Sigma s focus orbitals focus electron density between nuclei, holding them together. We call these bonding orbitals. Sigma star s focus electron density away from the bonding region, pulling the nuclei apart. So we call these anti-bonding orbitals. So if we take the case of two s orbitals and we consider their atomic overlap, the possible molecular orbitals they'll make could be anti-bonding, bringing the two nuclei apart, or bonding, overlapping, and bringing the nuclei together. We can picture this for p orbitals as well, forming an overlap along the internuclear axis or an anti-bonding orbital along the internuclear axis, And we can extend this to side-to-side interactions like we've seen before. So, relative energy levels of atomic molecular orbitals are typically shown in what we call a molecular orbital diagram. Atomic orbitals of one atom are shown on the left, and those of the other atom are shown on the right. Each horizontal line represents one orbital that can hold 2 electrons. Molecular orbitals formed by the combination of atomic orbitals are shown in the center. We use dashed lines to show which of the atomic orbitals combine to form the molecular orbitals. For each pair of atomic orbitals that combine, one lower energy bonding molecular orbital and one higher energy anti-bonding molecular orbital result. Electrons are filled into these molecular orbitals using the Aufbau principle. So we're going to fill lower energy orbitals first, where electrons are going to spread out among degenerate orbitals. So those are orbitals that have the same energy before we pair them off. And each orbital is going to hold a maximum of 2 electrons with opposite spins. Here we can see our Aufbau principle. If we had 2 electrons in a 2s orbital and 1 electron in a 1s orbital, we're first going to put 1 electron in this bottom energy level. We'll next pair it off. Then we'll move up to the higher energy level and put another electron. If we look at the example of H2, we can see that we have 2 electrons in our lower energy bonding sigma 1s orbital. That's going to predict that H2 will be a stable molecule with a bond order of 1. Diatomic helium, on the other hand, has 2 electrons in an antibonding orbital and 2 electrons in a bonding orbital down here. These are going to cancel each other out, so we wouldn't predict that diatomic helium would be stable, and it is in fact not. Bond orders. So an electron contributes to a bonding interaction if it occupies a bonding orbital, and it contributes to an antibonding interaction if it occupies an antibonding orbital. The bond order is calculated by subtracting the destabilizing antibonding electrons from the stabilizing bonding electrons. Since a bond consists of 2 electrons, we divide by 2 to get the bond order. So bond order is the number of bonding electrons minus the number of antibonding electrons divided by 2. You'll see that this actually does allow for there to be fractional bond orders, such as 1.5 or 2.5 or something like that. In molecular orbital theory, sigma orbitals are usually more stable than pi orbitals, but not always. Atoms with 3 or fewer electrons in the p orbitals, so lithium through nitrogen, we observe a different pattern in which the sigma p orbital is higher in energy than the pi p set. This switch in orbital ordering occurs because of a phenomenon called sp mixing. And xp mixing occurs when the s and p orbitals have similar energies. So it's not really important to understand s and p mixing, but just to know that this sigma 2px orbital is going to be higher in energy than the pi 2py and 2pz orbitals in cases where we have lithium, beryllium, boron, carbon, and nitrogen. And then from oxygen on up, we're going to see the pattern that we would expect it to have in all those cases. So that means that in the case, a more complicated case here, where we're trying to make diatomic atoms, we're going to need to move this sigma p up above these 2 pi orbital molecular orbitals here. So let's look at the case of oxygen. Oxygen has a 2s atomic orbital. These two are going to combine to form these sigma 2s and antibonding sigma star 2s orbitals. These two will cancel each other out. Therefore, the 2s electrons really aren't participating in bonding in the case of oxygen. If we go up to our 2p atomic orbitals, when they combine, they form 3 bonding orbitals, the sigma 2px and the pi 2py and the pi 2pz. We're going to fill all of these up, giving us a bond order of 3. But then we still have 2 electrons that we have to put into these antibonding orbitals using the Aufbau principle. We'll put 1 in each one, and that's going to reduce our bond order down to 2, giving us the double bond that we would expect oxygen to have. Band theory. So, in a solid, a huge number of atomic orbitals may be combined into molecular orbitals. When n valence atomic orbitals, all of the same energy and each containing 1 electron are combined, n divided by 2 filled bonding orbitals and n divided by 2 empty antibonding orbitals will result. The allowed energy levels for all of the bonding orbitals are so close together that they form a band called the valence band. Likewise, all the antibonding orbitals are very close together and form a band called the conduction band. In order to conduct electricity, electrons must move from the filled valence band to the empty conduction band. The size of the band gap determines how easy it is to move electrons between the bands. In conductors, the band gap is very small. In an insulator, the band gap is large. Semiconductors have moderate band gaps and conduct electricity only under certain conditions. So we can see now that using molecular orbital theory, we have a theory behind conduction that allows us to determine whether or not something's going to be an insulator, semiconductor, or conductor, if we can get a sense of how large this band gap between this valence band and this conduction band is. It is kind of interesting to note that this is temperature dependent. So semiconductors, under really cold conditions, we can actually decrease this band gap down so that we get good conduction between them.